Hi folks, this is Maria and I'm going to talk a little bit about valence electrons and most common ions. I'm going to start by talking about the difference between core and valence electrons. Then I'll talk a little bit about the octet rule. I'm going to then talk about how valence electrons connect to the most common ions, and then we'll wrap it up. So let's start with core electrons and valence electrons. Valence electrons are electrons that are found in the outermost energy level. They're the ones that are involved in bonding and ion formation. So they're going to be the ones that are actually way more important to talk about most of the time. Core electrons are electrons found in any other energy level other than the outermost one. So not all elements have core electrons. There's only going to be like a little bit more time that we end up talking about core electrons this year, but it's an important term to know. Let's practice identifying valence versus core electrons by looking at these different cards. So I'm going to start with, I've got calcium here, and if I'm looking for the valence electrons on calcium, it's just the two that we find in the very outermost shell. So these ones. Now if I'm looking at helium here, it only has one shell, so it's actually still 2 is the answer here. All right, what about core electrons? Well, if I'm looking at core electrons, I know it's electrons that are found in any other energy level other than the outermost one. So it's going to end up totaling all of these electrons here. You'll notice that I excluded the nucleus. So it's essentially every single one found here otherwise. Helium, on the other hand, because it's so small, actually only has valence electrons. It does not have any core electrons. But yeah, just good to know. Awesome. Octet rule. Let's talk about that. So the octet rule is about losing or gaining valence electrons to have a full outer shell for stability purposes. In other words, it really means having a full outer shell that looks a lot like a noble gas's outer shell. So for row 1, this means having 2 valence electrons. For elements in rows 2 and 3, this means having 8 valence electrons. So you may have heard of this referred to as the 2-8-8 rule if you've heard of this in the past. And if you haven't, that's okay. We're learning about it now. Beyond the first 3 rows of the periodic table, electron shells can hold more than 8 electrons. So if we were looking at a 4th shell, it could actually hold more. But we're going to kind of put that to the side. We just want you to know, like, the first 3 rows are honestly what we're going to use the most in chemistry this year. And so that's why we're teaching about these. I do want to point out with the octet rule, you'll see that if I'm looking at these first 3 elements that are in the noble gases, helium, neon, and argon, you'll notice that because they have full outer valence shells, they all share a similar property. They don't gain, lose, or share electrons. That makes reasonable sense. They already have full outer valence shells. Versus if I'm looking at something like oxygen, oxygen on the other hand has 6 in its outermost shell. And since it has 6 in its outermost shell, you'll notice that it tends to gain or share 2 electrons. Let's talk more about that in just a moment. So the octet rule ends up connecting back to the most common ion. And the reason for that is the most common ion for each type of element is going to be dependent on how many valence electrons an atom has, and then the fewest number of valence electrons to either lose or gain to fulfill the octet rule. So if I look at the sodium atom, if I look here, there's 1 valence electron for sodium. So there's 2 options. Either it could lose that 1 valence electron, or I gave away the ending there. That's okay. I could lose the 1 valence electron, and to end up having a full outer valence shell because it now has that full outer valence shell, or it could gain 7 more. And it turns out that if we're thinking about the fewest number of valence electrons, the 7 more would not be very favorable, not energetically favorable. That's gaining too many electrons. And so this is not an option. Sodium 7 minus is not an option. You will never see in this class an atom or an ion that has a plus or minus charge larger than 4. That would be the maximum that we would end up with. So it turns out that this leads to some patterns within the periodic table. And so we can actually figure it out with just a periodic table. I'm going to use some more of those Bohr model diagrams that I was showing you, but it's a pretty common thing for us to be able to just hand you a periodic table and figure it out. So first thing you do is you figure out how many valence electrons an element has, and this is going to correspond to the column that it's in. It's not always labeled exactly like this. You will see this always be column 1, this always be column 2, but you might see this being labeled column 13, 14, 15, 16, 17, 18. And my rule of thumb is that if you just say that the valence electrons is equal to the ones place for each of the columns, that's all you need when going through. Once you then know the valence electrons, you go with either the least number of valence electrons to lose or gain to get a full valence shell. So if you look, there's some patterns in the most common ions. 1A all have +1 charges. 2 has +2 charges. If I'm looking at 3, it's got 3 valence electrons, so we've got a +3 charge. 4 ends up being a little weird. We'll come back to this like later on when we're talking about ionic naming, but 4 could be plus or minus 4. These two also have other options. 5 have 3 minus because there's 5 valence electrons, so it's easier to gain 3 electrons than lose 5, and then so on and so forth. You'll notice that in this last one, because it's noble gases, that they're not really losing or gaining anything, and that's because they've already got that full outer valence shell. Okay, I do want to quickly talk about this group here. So if you remember from when you're coloring your periodic tables, this is our transition metals. You will not be expected to predict the charge on any of these when going through, and that's because there's some weirdness around transition metals. They often have more than one possible, like most common ion. These are some of the most common ones, but there's certainly more out there. So I wanted to show you real quick with the fluorine what that looks like. So if I'm looking at fluorine, fluorine normally has 7 valence electrons. So in order to have a full outer shell, it gains 1 more electron, meaning now it's got 8. And so fluorine is F minus. If I look at sodium, it has 1 in its outer valence shell. It loses 1, and so therefore it would be sodium +1. All right, great. So let's do a little practice. So I've just got a periodic table here. If you want to pause the video, see if you can figure out, there's 2 of these that are a little bit sneakier when going through. I'll talk about them in just a moment, but if you want to pause it, try it for yourself, and then unpause to hear me talk about the answers. Okay, great. So if we're looking at the example here, phosphorus is in column 15, so it has 5 valence electrons. It could either gain 3 or it could lose 5, and because it's easier to gain 3, then it'd be P3 minus. Ne, this is one that's a little sneaky because it's a noble gas. It doesn't actually have a most common ion. So there's no common ion. It already has a full valence shell. All right, magnesium. Magnesium is in column 2, so it has 2 valence electrons. It could either lose 2 or it could gain 6. It's easier to lose 2, so it's going to be magnesium 2+. And then carbon. Now this is a sneaky one because number 1, carbon doesn't really form a lot of ions. So if it were to form an ion, it is in column 14, so it's got 4 valence electron. We'll talk about why carbon doesn't normally form ions when we get to bonding later on, but If it were to form an ion, because carbon is also a nonmetal, you'll notice that nonmetals have negative, have anions, and metals have cations as a general rule. And so carbon would actually be -4 because it's a nonmetal. If we were to ask you something in this particular column as a general rule, you just want to keep that in mind. If it's +4, it's going to be the metal. So tin and lead can be +4. That's a not uncommon state for them. And then carbon, though, if it had to be an ion, it would be 4-. Okay, so that's it. So that's some examples. You have some practice right here. Go through, figure out the most common ion for each element. You're probably going to want a periodic table. If there isn't a common ion, just briefly state why. All right, we will see you soon. Write down any questions you have and have a great night.